A couple of reminders before we get started showing what we want to show is that when we're just looking at the XY plane from above, we don't want to say left, right, up, and down anymore because up and down should be measured by Z. What we're going to be using all the way through the semester is that side is west, that side is east. What used to be down is now south, and that's now north. So just a reminder, west, east, south, north. And the second reminder is just what we're trying to show. What we're trying to show is the formula that delta Z equals M times delta X plus N times delta Y. Now we could do this algebraically, but there's no intuition involved algebraically, and it won't mean anything, and we want the geometry to be there. We actually want it to actually be there when we do the tables too, but we're going to do it geometrically first. So what we're going to do is remind ourselves is what this is. This is for a linear function, and what we want to know is when we move from one point on a plane to another point on the plane, how do we calculate the change in the elevation? So here we go. What I'm going to do, this diagram actually can be made much more general, but I think I'm going to do enough so that we can live with what we have. I want our plane to have positive slopes in each direction. In order to do that, I have to put the negative x-axis over here, and the positive x-axis will go that way. I want the negative y-axis to go this way, so the positive y-axis will go that way, and then the z-axis will go there. Now, in general, to plot planes, it's enough to just find the intercepts. So if I find the intercepts for the plane, the nice thing about plane, if you take any 2 points on the plane, the line connecting them is in the plane. So that line segment is in the plane, that line segment is in the plane, and that line segment is in the plane. So remember, the plane is just going to be just this piece, this piece, this piece. And let's actually make that brown. So every time we draw a piece of plane, it'll be in brown. There we go. So what I'm going to do is pick a point on the plane and then try to calculate the change in elevation from this point to this point. Now, you see this brown line here? It actually goes due east, from west to east. So what I'm going to do is, starting from this point on the plane, I'm going to walk due east, which is going to be parallel to that. So I'm going to try as hard as I can to draw something that goes parallel to that, and that's due east. If I start here and I want to walk due north, remembering that this line here is due north, I'm going to try to stay parallel to that like that, which is good. Now from this point and this point, I want to draw points that are not on the plane that will give us some perspective. So from this point here, I am just going to go all the way down to the y-axis. And from this point here, I'm going to go all the way down to the x-axis. Now, from this point here, in the xy plane, I'm going to draw something that's due west. I think if I draw it sort of like that, that'll work. From this point here, I'm going to draw something that goes due south. Let's see here. I think this needs to be a little bit more this way. And then like this. And if I've drawn it just right, probably like that, then this line here will come straight down. And like I say, the problem is as soon as you try to draw these so that things aren't exactly parallel, you get in trouble. But you get the idea, right? What we have in the bottom here is a rectangle. What you have on top is a parallelogram that's actually in the plane. And what we're trying to do, remember, is to calculate the change in elevation from here to here. Now I'm going to label a couple more things. This thing right here is actually a change in the y value while x is being held constant. This distance right here is a change in the x value while y is being held constant. And now we can use the fact that this right here is a line that's parallel to this line. We know its slope and we know the change in the x. So let's start labeling the changes in elevation. When I walk due east from this point to this point, the change in the elevation is going to be the slope of this line times delta x. That's actually just Calc 1. So the change in the elevation here is going to be m delta x. Now, how are we going to calculate the change in the elevation? While staying on the plane, we're going to walk due east until we're at the same longitude as this one. Then we're going to turn our little cells north, and then we're going to walk north. So I still need, in order to calculate the change in the elevation, I need this change right here, which, by the way, is exactly the same as the change right there. Now, what is the change right there? Well, it's the slope of this line, which is n times delta y. So the change in elevation here is n times delta y. So the change in the elevation here is n times delta y. And now we can actually write down our conclusion. That the change in the elevation while walking from this point to this point, remember what we did. We walked due east until we were at the same longitude, and then we turn north, and then we walk up. The first change in elevation while we were walking due east is just m times delta x. The change in elevation as we turn north and walk this way is n times delta y. We can show this algebraically real easy, but we really have to have this picture in our head when we're actually imagining what's going on. And that's why the most important equation we're going to see this semester is true.